All right, let's get into it. Today, we're putting on our detective hats and diving into the world of mathematical mysteries. We're on a case to figure out how things change, things like the speed of a rocket or how a population grows. And our number one clue? It's something called a differential equation. So let's start the investigation. So here's the big question, the central puzzle of our entire investigation. Imagine you know the exact speed of a car at every single moment of its trip. Could you work backward from that information to figure out the exact path it took? The answer is a huge yes, and that's the fundamental reason differential equations are so powerful. But to find that answer, we need a special tool. This is our magnifying glass, our fingerprint kit, all rolled into one. It's the differential equation itself. Think of it as the secret language that perfectly describes the relationship between something and how fast it's changing. Okay, so let's start by examining our most important piece of evidence. What in the world is a differential equation, anyway? At its heart, it's really just an equation. But it's a special one, because it contains a function and its derivatives. So if we say y is a population of rabbits, then dy by dx is how fast that population is growing. This equation connects the two. It's a direct clue about the dynamics of change. Now, any good detective knows you have to be able to read the evidence properly. So let's learn how to classify these equations. That way, we'll know exactly what kind of case we're dealing with each time. First thing we look for is the order. This is super simple. It's just the highest derivative you can find in the equation. If you only see a dy dx, it's a first-order equation. That's what we'll mostly be tackling. If you see a d squared y over dx squared, you're looking at a second-order equation, which is often used for things like motion and acceleration. And right alongside order, you've got degree. This is just the power of that highest order derivative. It gives us a few more subtle clues about how complex the relationship is. For today, most of the cases we'll see will have a simple degree of 1. So once we solve an equation, we get a solution. But hold on, there are actually two types. And understanding the difference, well, it's like knowing the difference between a vague sketch of a suspect and a definitive positive ID. So on one hand, you have the general solution. This is our vague hunch. See that plus C there? That's an unknown constant, which means this solution actually represents a whole family of possible answers. But then you have the particular solution. This is the positive ID. By using some extra info, what we call an initial condition, like knowing that y equals 2 when x is 0, we can figure out exactly what C is and lock down the one specific answer we need. All right, it's time to learn our primary investigative technique. For the kind of equations we're looking at today, those first-order ones, our absolute go-to method is called separation of variables. And this method is just so logical. Step 1, you separate your suspects. You got to get everything with a y on one side and everything with an x on the other. Step 2, you interrogate both sides by integrating them. And finally, step 3, you rearrange everything to solve for y and get your final answer. And please, don't forget that super important plus c, our constant of integration. Theory is one thing, but a detective proves their skills out in the field. So let's apply this new technique to a live case file. We're going to solve this thing together, step by step. Here it is. Here's our case. dy dx equals 2 times x times y. So we've been given the rate of change. Our job as detectives is to find the original function for y. So you're looking at the evidence, you've got your three-step method in your head. What is the absolute first thing we have to do here? Exactly. We separate the variables. We use a little algebra, divide both sides by y, multiply both sides by dx, and just like that, the y terms are on the left and the x terms are on the right. Our suspects are in separate rooms, ready for questioning. Perfect. The variables are separated. What does our procedure tell us is the next logical step to get us closer to cracking this case? You got it. We integrate. We apply the integral sign to both sides of the equation. This is that key mathematical step that reverses the derivative and helps us work our way back to the original function. And after we do the integration, here's what we get. The integral of 1 over y is the natural log of y. The integral of 2x is x squared. And, crucially, we add our constant of integration, that plus c, on one side. We're almost there. Now, to close the case for good, we need to get y all by itself. To do that, we make both sides the exponent for the base e. That e cancels out the natural log, and it leaves us with our beautiful general solution. y equals some constant, c, times e to the power of x squared. And with that, case closed. So we solved a math puzzle. That's cool and all, but why does this matter? Let's zoom out for a second and see just how powerful this detective skill is in the actual real world. Look, this isn't just some abstract thing you do in a classroom. Differential equations are the backbone of modern science. They're used in physics to calculate motion, in biology to model population growth, in chemistry to track reaction rates, and even in economics to build financial models. So by learning how to solve these equations, you haven't just learned a new piece of math. You've actually gained a really powerful new tool for describing, understanding, and even predicting how the world around you works. You now hold the key to unlocking the story of change itself, whether it's in science, finance, or anywhere else. So my final question to you, detective, is this: what mystery will you solve first?